So the subject of this lecture is an introduction to regression. Now, it is a multifaceted subject and I don't want to trivialise it. It's a serious subject, but you can view it, at least in part, as an extension of high school maths. Okay, that said, it is an important subject and it marks really the starting point of both mathematical statistics and financial research methods. Okay, and it's really the beginning of life beyond frequency tables, because if all there was in life and in financial research methods were frequency tables and the things we saw in the first lecture, the subject would become very sterile very quickly. Okay, and here is the beginning of where the subject really comes into its own and becomes a proper subject. Now, beyond that, the subject of regression is important for dissertations, and it's something that is relatively easy to apply if you obtain some quantitative data, and you can relatively easily show a sort of professional standard of analysis and a systematic approach. Now, that's always important. I suspect in the sort of COVID situation with perhaps limited access to your supervisor, that might become even more important than usual. Okay, the ability to analyse a numerical data set systematically and professionally. So it's important for dissertations and the important starting point for whether to. So in terms of background reading then, so I've recommended chapters 4 to 8 of this textbook here. Now I'm sometimes a little bit rude about this book. It is a little bit of an undergraduate potboiler, but it does do a very good choice of topics to cover. The serious point I should say, I don't want, because you aren't imported, to libel me. The serious point is that you have lots of resources available on the module. So you've got these lecture recordings, the PDF lecture slides and the PDF study book, and I've designed it so that as much as possible the material is self-contained. Now this is a textbook. I'm also planning on turning my notes into a textbook myself. Okay, so you've got this reference here for background reading, but hopefully these lecture notes should be relatively self-contained and they will hopefully also spawn a textbook in due course. So that is all true. It's obviously very unideal situation this year with COVID, hard for students, hard for staff as well. What I would say is that students of mine have successfully taught themselves from just the PDF slides in the past. This time, I know it's more difficult with the class contact, but you do have more resources to try and make up for that a little bit. And as I said before, students of mine have done very well in the past, so I want you to have confidence that you can continue that. So regression is extremely important then. So it is interesting as well, I think, and it's important to sort of say that, but I think the main thing is it is important, especially with a view towards dissertations. Now, I said there the subject underpins nearly all mathematical applied statistics, so it's the first serious starting point for the subject. The subject also underpins important things like econometrics and financial econometrics and financial research methods. Rigorous statistical techniques are often an integral part of MSc dissertations, and I suspect this is important in ordinary times and might become even more important now if you've got limited access to a dissertation supervisor. Beyond this, high-level financial research is inherently quantitative, and what you've got in this course is a sort of basic introduction to that. That's not to say that finance is, not to deny rather that finance is inherently subjective, but even if you sort of calculate subjective benchmarks, that's inherently quantitative. Okay, so some people like maths because they think it's always objective. Finance isn't like that, but I suspect it's inherently quantitative at a decently high level. Finance is then much more than just applied mathematics, although that was my route into it, and I suspect this is sort of true and even more true over time. High-level research in the social sciences is increasingly quantitative in nature. If it's mathematical now, it's going to get more mathematical in the future. So, in terms of what I've rather pompously entitled mathematical good advice, then, so maths is not always easy, and it's something that sometimes unduly scares students, but it's often easier than it first looks, and often the questions asked are deceptively simple. We've got regression, which is this important starting point for various topics, okay, but in part at least it is just an extension of high school maths. Now the basic question in regression is always what happens to y x increases, decreases, or nothing at all. So again, quite a simple-minded question, and you can sort of view it in this way. It's just a more advanced version of high school maths. Now the next couple of slides are a repetition of things you've seen in the first lecture, but I just wanted to sort of reinforce this. And beyond this sort of repetition of school level maths, what I think is really neat is that you can emphasize some of the core concepts graphically. Okay, so there's a wad of equations to come, but I think it sort of makes it all more believable and more friendly if you can sort of appreciate that there's sort of basic graphs that sort of underpin all these concepts. Okay, so these graphs just illustrate then the basic question: what happens to y as x increases? Does it increase? Does it decrease? Or does nothing at all happen? So here we have then a sort of cartoon example of a positive gradient. So the idea here is that as x increases, equivalently x decreases, y decreases. And this is a sort of basic idea that you have hopefully seen before in high school maths. So the basic idea does sit behind regression. So some of the tests are essentially an abstraction of this basic graph. And we had a sort of example that we discussed in the previous lecture. So suppose you had something like x being the fuel price and y being the supermarket price of food. So you can imagine that as x increases, so as the fuel cost increases, the cost of food in the supermarket will also increase. Equivalently, you might also expect to find that as the fuel cost decreases, then you might also see the price of food in the supermarket decrease at the same time. Okay, so lots and lots of examples of this basic concept in all kinds of areas of finance and economics. Okay, and as I said before, you've got this sort of relatively simple cartoon straight line graph that illustrates this, and regression is just a different version of this with some Greek letters and some equations, but it's essentially just a different way of drawing the same graph, which you'll have hopefully seen before at high school in any case. So we've got a second cartoon example here of a negative gradient. So it's the sort of mirror image, if you like, of the previous graph. So the idea here is that as x increases, y decreases. Equivalently, as x decreases, y increases. And again, all sorts of examples of this phenomena throughout finance and economics. So the example we discussed in the previous lecture before, so if you imagine as x being the fuel price and y being the profit of the haulage company, so as the fuel price increases, you might naturally expect the profit of the haulage company to decrease. Equivalently, as the fuel price decreases, you might expect the profit of the haulage company to increase. Okay, so again, lots and lots of fairly common sense examples of this phenomena throughout economics and finance. And to repeat myself, okay, what you've got here is that this is just a sort of graph that you'll have seen before at high school maths. The same basic principles underpin some of the regression techniques we'll talk about in this lecture and the lectures coming up. Okay, you might see some equations and some Greek letters, but all it is just a different way of drawing this picture that you'll have hopefully seen before in high school maths. So the other possible example is this example where you have a zero gradient. So the idea here is that if you have high values of x, nothing at all happens to y, and if you have low values of x again, y. Now this is a sort of cartoon example, and it's probably particularly extreme in this case, but the basic idea would be that if you graph these two variables, there'd be no obvious relationship between them. Okay, and this is again a sort of cartoon example, but this does underpin some of the regression techniques we'll talk about in this lecture and in the next few lectures. And again, what you might see when you sort of go through these formal regression methodologies, you might have some equations and some Greek letters, but it's just a different way of drawing the same graph. Okay, and this graph, again, a version of this you'll have seen before in high school maths, so it shouldn't ultimately be that complicated. So regression is a potentially hard subject, and it's an important subject, but lots of these basic questions are deceptively simple-minded. Okay, and as we've seen here, you can illustrate a lot of the main concepts just from the sort of basic straight line graphs that you will have seen before in high school maths. So assuredly, I do not want people to be unduly worried about this. Now, I wanted to hear sort of real data examples. So those previous three graphs are sort of cartoon scenarios of the idealized thing working perfectly. Now, a real data set will be much more imperfect than that, okay? But the same basic idea applies. So here what we've got a plot of the gold price. So all this means is essentially an adjustment has been made for inflation. And once you do that, what you see is you have this correlation and the stock price. So a straight line, you can sort of see from this that there is a tangible relationship between the two, and we'll discuss this in more detail in the lecture. And it's not just a sort of case of eyeballing the graph and saying that these things are negatively correlated. A discussion and a consideration of the financial context also means it's natural in this case to think that the real gold price and the real stock price will be negatively correlated. So if stock prices going up, people might move from gold to buy stocks because they think they can make a speculative profit. Equivalently, if stock prices are decreasing, there might be a flight to quality and a sudden rush to buy gold, and this increased demand might in turn increase the gold price. So in both scenarios, you get a negative correlation between the real gold price and the real stock price, grounded in a tangible financial mechanism. Okay, so the basic rule then with this or any other maths is don't panic. So these regression problems that we're going to see later in the lecture can look a lot harder than they really are, but again they're grounded in relatively simple observations that are in essence just an extension of things you've seen before at high school maths. So beyond all the equations and all the terminology and sometimes fairly awful textbooks, basic question remains: what happens to y as x increases? Okay, and it's just essentially a repetition of these three cartoon graphs, which are themselves a repetition of high school maths. So on occasion, sometimes there's some unfortunate use of jargon. So Gujarati and Porter in their book distinguish between two cases here: two variable regression model and a multiple regression model. That's not the most systematic way of as a subject, and I'm really not very happy about the presentation in this book. So despite this apparent difference, the mathematical methodology and the regression fitting commands in both R and E views and any other software worthy of the name will essentially be the same. So this distinction here is quite artificial, actually exaggerates and inflates the difficulty of the subject. So just to sort of reinforce that point then, I want you to sort of be aware a little bit of cosmetic differences in notation and jargon that can just inflate and exaggerate the difficulty of the subject. So some authors use different terminology and notation for essentially the same thing. Often it's a sort of product of trying to make the thing more accessible, you actually make it harder. So in Gujarati and Porter, they talk about this two variable regression y, second variable x, two variable regression model y, second variable x2, third variable x3, and a multiple regression model where essentially you have three variables, so more than three x variables in the model. Now, equations usually look harder than they really are. Now, what I wanted to emphasize here is that in terms of mathematical methodology and commands in either R or E views, these are all special cases of the multiple regression model on the slide. So it's actually easier if you just think of this in terms of the equation on the slide, and the other two equations are just special cases of this. And this is an example, I think, of Gujarati and Porter trying to make this subject more accessible and less scary for students, actually make it harder. This equation on the bottom is the only one you really need, and again, same set of software commands in each case.